Okay. I hope you guys can hear me okay.
Yes.
Yeah, good. I'm just letting people in and we'll start once we see that most of you guys are here. Ooh. Wow, everybody's here almost. It's pretty good. Okay. All right. So I hope you guys are doing okay, staying safe, trying to focus. Not so easy. My plan today is to go through the slides I set up on Leia yesterday briefly, and then after that to run through that pretty intense looking example, which is hard to read by yourself probably. So I'll go through that and we'll see how we're doing on time, and after that we're going to look at implicit differentiation. So let's jump in. So let's look at those slides. There we go. All right. So last class, which seems to be like 2 years ago, we looked at the chain rule in several variables. So I want to simply just restate the theorem. So if we have a differentiable function u of m variables, x1 to xm, and in turn, each of these variables is in fact a differentiable function of variables t1 to tn. So this is a composition. So u will be a differentiable function of t1 to tn. And we have an expression that gives us the partial derivatives of u with respect to each one of t1 to tn, which is what you see on your screen. So del u del t I is del u del x1, del ti, plus, and so on and so forth, right up to the last variable xm, del u del xm, del ti. Okay, let me just let some people in here. Welcome to all. I think almost everybody's here. That's great. Okay, so now the formula that you saw is a shorthand, so it's missing part of the information is where you're supposed to evaluate the partial derivatives. So if we write that all in, we get this intense looking chain rule. So let's say you want to evaluate del u del ti at some point, so some values a1 to an for the variables t1 to tn, then you have to evaluate all of these partial derivatives in the right place. So let's take a look at an example. So it's much simpler to actually just look at one concrete example than try to parse this. So let's move on to the next slide. So here our function u is a function of 4 variables. I didn't use x1 to x4, but it's in the formulation that you saw. These would be x1, x2, x3, x4. So it's x, y, z, and w. So u is x squared plus y squared plus z cubed plus w cubed. And you see that x, y, z, and w are functions of t1 and t2. Okay, so x is t1 plus t2, y is 3t1 minus t2, z is t1 squared, and w is e to the t2 plus e to the t1. So u is a function of these 4 variables x, y, z, w, and all of these 4 variables are themselves functions of t1 and t2. So that means that u is actually a function of t1 and t2. So in theory, we can compute del u del t1 and del u del t2. So I'll stick to del u del t1. The other one is just exactly the same. So what does the chain rule tell us? It says that del u del t1 is del u del x del t1, right on up to del u del w del t1. Okay, so I'm pretty sure all of you, or at least 3 weeks ago, could differentiate all of these pretty straightforwardly. So if you do that and you just replace the expressions, you will get that del u del t1 is the expression you see. So 2x times 1 plus 2y times 3z squared plus 2t1 plus 3w squared e to the t1. Okay, now I said this in class, it looks strange because obviously we should be getting a function of t1 and t2 only, but here we have x, y, z, and w. So if we only want t1 and t2, we just replace by the values that we know we have for these, okay? So this is what I did here. So I just wrote down explicitly the partial derivative of u with respect to t1 in terms of those 2 variables only. But often it's not necessary to do this and to evaluate, let's say. So let me just show you the next slide. So I'm going back to the first expression, which still has x, y, z, and w, okay? And now suppose we're asked to find the value of del u del t1 at the point 2, 3. So these are the values of t1 and t2. So first I need to evaluate each of x, y, z, w at this point. That's easy. You just replace in the definitions of x, y, z, and w, and you're going to get the values you want. And in the del x, del t1, and so on and so forth, you can again just replace t1 and t2 by 2, 3, and you can just compute the full value. I didn't simplify the expression there. We don't care about that. So you can evaluate this way. Okay, so I think I did this example in class before, and I stopped right there. So let's look at a second example, which is a bit more involved. So here we have a function z of x and y, and x and y are both functions of r and s. So x is r squared plus s squared, and y is 2rs. And we're asked to find expressions for del z del r. So z is a function of r and s via x and y, and a second derivative, so del 2z, del r2. So this is the derivative of our first expression with respect to r, so a second time. And now the thing is that we don't know what z is as a function of x and y. So the best we can hope for is have del z, del x, del z, del y, and all these expressions, we won't know what they are, so we'll just have to stick with those, okay? Now, there was absolutely no way I could write this down to type it up. It's just a mess, so that's why I sent you those handwritten notes. So now I'm gonna do the actual computation live, if you wish, to explain all the details. So let's go and take a look at this. Let's go here. Hopefully this will work out. Okay. Okay, so hopefully you see this. So here's our example. We have our function z. Yeah, that works. It's a function of x and y, which are both functions of r and s, like this. Okay, so what does the chain rule tell? Let's just write down what x is. X is r squared plus s squared, and y is 2rs. And so what does the chain rule tell us? If I want to compute del z, del r, chain rule says this is del z, del x, del r, plus del z, del y, del r. Okay, so again, these guys here, I don't know what they are because I don't know what z is. Okay, but I can certainly compute these guys here. Okay, so I've got del x, del r is 2r, del y, del r is 2s. So putting this together, I'm going to get that del z, del r is del z, del x times 2r plus del z, del y times 2s. Hopefully that's all good for you guys. Okay. All right, so that's the first thing. So that's the best we can do at this point, okay? Now, what I want now is to find del 2z, del r2. Okay, that's the trickier one, okay? So what is this? This is the second derivative of del z, of z. So this is what? This is the derivative with respect to r of del z, del r. This is what this is, okay? So I'm going to compute the partial derivative with respect to r of this whole thing, okay? So here we go. So I'm going to, let's try this out. All right, so what I want is to compute del r of this thing, del z, del x times 2r plus del z, del y times 2s. Okay, so it's a sum. So it's just, this is just a derivative, right? So I can just split it up first as a sum. So del r of del z, del x times 2r plus derivative with respect to r of del z, del y times 2s. Okay, so far so good. Okay, so I can factor out my 2 here. I'm actually pointing at my iPad, which of course you can't see, so sorry about that. This is very strange. 2 times del r of del z, del x times r, plus, and I can factor out that 2 again, 2 times del r, del z, del y times s. Okay, so here we go. So look at this expression. You're taking a derivative of a product. So, product rule. Oh, by the way, I'm going to save these slides that I'm creating, and they'll be on Leia. So the video also, but the slides themselves will also be there. So, okay, so this is a product. So this is derivative of the first times the second plus first term times the derivative of the second term. Okay, and then I do the same with this guy. So this is 2 times del R of del Z del Y times S plus del Z del Y times del R of S. Okay. So again, all I did is use the product rule. I haven't done anything really fancy. I just know I'm doing a derivative here. Now here's where it gets a little different. So let's just take this thing here. And go here. All right, so, okay, so let's do the easy things first. So let's look at this guy here, del R of R. That's a straightforward derivative. That's just 1, right? So I can just, let's be fancy. Let's do that. Let's do that. So this guy here is just 1. There we go. Okay. What about this guy here? So this is the derivative with respect to R of S. These are 2 independent variables. I'm taking the partial derivative of S with respect to R. S is just a constant, so that's 0. So this is what I get. Okay, so let's rewrite that. So this is 2 times partial derivative of del Z del X times R plus del Z del X plus 2 times del R of del Z del Y times S, and that's 0, so that's gone. Okay, all right, so now for the very last thing, if you look at this expression here, so you're taking a derivative with respect to R of the function del Z del X. Now, del Z del X, this is a function of X and Y, right? So we have del Z del X, function of X and Y, which are functions of R and S. So to compute this partial derivative, what do I need to do? I need to use the chain rule. Okay? So let's just take this. Expression right here. Let's go down here. Okay, so I'm going to use the chain rule to evaluate this partial derivative. So how does it go? This is 2 times. Okay, so del R of del Z del X. This is del X of del Z del X times, and I've got a brain cramp right now, del X del R plus del Y of del Z del X times del Y del R. So this is just this guy here. Yeah, I know. I don't hear you, but I can feel your dismay at this. But if you just do it step by step, it should be okay. Let me just see if hands up. All right. Okay. Oh, geez. There you go. Sorry, I'm still trying to get. Okay, good. Welcome. Okay. So again, I have to use the chain rule to compute this partial derivative. So if you find this confusing, what you might want to do is just replace this by another name, call it, let's say, V or W, and just rewrite down the chain rule in terms of that, and you'll see this is what you're going to get. Okay, so this is, I'm just going to rewrite my del Z del X here. So here we go. And now for the second part, so this is the second bracket, which is here. Okay, so again, del R of del Z del Y, this is a chain rule. So I'm going to apply the chain rule again. So this is del X of this function times del X del R plus del Y of this function times del Y del R. All of this is multiplied by S. So that's our next step. Okay, so that's actually the hard part. This is the only harder part in the whole thing, okay? Last thing that you want to do is just reroute it properly. Okay, so let's take a look at what this is. This is the second partial derivative with respect to x, so twice. So I'm just going to rewrite that in the usual way. So this is del 2z del x2. Del x del r we computed earlier. That was 2r. We can do that. Plus this guy here, del y del z del x. This is written as del 2z del y del x. Del y del r we found is let me go check. S, right? Yes. Like this. And all of this is multiplied by r. Yeah, I know. This is about the worst example I could use to start our COVID-19 teaching experiment, but that's where we are at. So sorry about that. It'll get a little easier after that. Okay, so this is this whole expression here plus del z del x, like that, plus 2 times. Now I'm going to rewrite this part here. So this is del 2z del x del y times 2r. Is that 2r correct? Let me just double check. Yes, it is. Okay. Plus del y, this guy here, del y del z. This is del 2z del y2. This is just a notation, right? It's the same thing. Del y del r we found is 2s. All of this is multiplied by s. And that's basically what we've got. Okay, essentially we're done. At this point, this is the best we can do. Okay? All right. Okay, so let me just save that. Okay, now I added a comment. If you looked at what I posted, because if you look in the book, this thing is phrased a little differently. So this is the expression we get. Now, suppose that the function we had to start with is nice. By this, I mean that the partial derivatives, the second order partial derivatives are continuous. So it's a very nice function. So you might remember Clairaut's theorem. What it says is that if you take the partial derivatives in any order, you get the same thing. So in this case, del 2z, del x, del y is the same as del 2z, del y, del x. Okay, so that means that you can actually simplify this expression. And I'll let you do it if you want. I don't know if this is okay. Let's try. So this is del 2z, del x2 times 2r plus del 2z, del y, del x, which is, sorry, the same as del x, del y. Let's write it this way, times 2s. All of this is multiplied by r plus del z, del x plus 2 times del 2z, del x, del y times 2r plus del 2z, del y2 times 2s, and all of this is multiplied by s. I won't finish it up. It's in the notes that I put later on, but that's the only thing that you can add here in this example that's of interest. Okay, so hopefully that works for you guys. Any questions? I don't see anybody. I don't hear anybody. I feel like I'm talking by myself, which I am.
I have a question.
Yes.
What you just wrote down on
Yep.
like the bottom half of the screen,
Yep.
like is this exactly what you wrote at the top of the screen, or is there something different about it?
Okay, so the only difference is I'll just use red here. If you look at this guy, I just rewrote it in the other direction. So I could actually now, at this point, what I could do is we can rewrite, right? We could put things together. Right? For example, so you see now that, wait, sorry, these two guys are the same, right? So if I just multiply out, I could rewrite these two terms together. That's basically the only difference.
Okay, I get it.
All right, good. It's nice to hear somebody. Thank you for the question. All right. Okay, so again, this example is sort of nasty. It just has a lot of stuff going on. It's sort of more theoretical because you don't know what z is in terms of x, y. That's what makes it hard. But if you actually go through the example and you can follow and see all the details, you're in really good shape. Okay?
Well, I just had a question.
Yep.
Can you go up in the previous page?
Yep.
So then, how come just the first small thing became the whole big thing?
Okay. The first, wait. This, in
like
this.
the part it says del over del r multiplied by del z over del x.
Yeah.
When you did the chain rule the second time.
Okay, yeah. So going from here to the next slide, right?
Yeah, I think.
Okay. So first of all, this is really important. When I write this here, look, you see, it's not a product, right? It's of. This is del r of what's inside. Okay, I'm applying the derivative operator. Like it's the same thing as, so it's the derivative of this. They're not multiplied. Okay, this is really important. Okay, so Okay, so let's go to the next slide to see how this worked out. Okay, I'll do a new slide here. I'll just do this part, which is the hard part, right? So I'll copy this. I'll go to the next slide here. Okay, so let's see what's going on here. Let's take that out. Let's take that out. Let's take that out. Sorry about that. What is going on? Okay, something's really fishy. Sorry about that. Okay. Let's remove that. Okay. I have no idea why this thing is not erasable. Okay. So I want to compute this. Okay. So this just for let's just rename del z del x. Let's call it u. Okay, just for the purposes of this. So what I'm trying to compute is del r of the function u, right? So that's the same as sorry, del u del r. Okay, so what does the chain rule say? So I have u function of x and y, and these are functions of r and s. So if you apply the chain rule to this, it says partial derivative of u with respect to x times del x del r plus del u del y times del y del r. So this is just the chain rule. Okay? So del u del x del r plus del u del y del r. Okay? So, but now let's just rewrite this. Rather than having u, I want del z del x. So let's just write this. So this is the partial derivative of u with respect to x. So that's the same as partial derivative with respect to x of u, right? Okay, let's do an extra step here. I'm just going to write that like that. Del y of u, del y del r. That's the same thing. Okay, this is exactly the same thing. But now I'm going to rewrite, instead of u, I'll just put the del z del x. So this is del x of del z del x of del x del r plus del y. This is del z del x del y del r. Okay, so this is what I got on my previous slide. Okay, so the partial derivative of del z del x with respect to r, applying the chain rule, will give you exactly this. Does that make sense?
Yes.
Sort of?
Yeah, better.
Okay, all right. So again, I'm applying the chain rule. This is just the statement of the chain rule if your function is, the dependencies of the variables are this way. And so I'm just writing out this thing. Maybe the difficulty is understanding part of the notation. You have to understand that when I'm writing del x of something, right? This means derivative with respect to x of what's inside. Okay, so this is what this means right over here. Okay. All right. Other questions? That's okay. All right. Okay. So I'm going to move on to something a little easier. I don't know if I'll have time to finish everything I want to do with implicit functions, but that's fine, okay? We're just starting and we're not going to stress ourselves. So let's just move on to implicit functions and implicit differentiation. Okay, so let's just go back to Cal 1 very briefly. Okay, so what's the, it's a simple idea, okay? So let's say that we have a function f, and we look at its graph. So it looks, let's say, something like that. This is the graph of f, like this, okay? And we're given a point, let's say a value of a, and I'm interested in the slope of the tangent. So that's easy, right? So slope of tangent at the point a f of a. What do? I compute the derivative and I evaluate at a. That's great. So I've got my slope of tangent this way. But suppose that we have a curve which is not a graph. Then what do? Okay, so here's a simple example. I give you x squared plus y squared equals to 1, a circle, right? This is not a graph, right? Okay, so if I'm asked to compute a tangent to this curve, then clearly this method that we saw just earlier is not going to work. So what do? Okay, so let's go back to our circle like this. X squared plus y squared. So let's say I want slope of tangent. So it's a simple idea. I mean, it's a deep idea, but the idea is it's easy to see is the following. So at most points, locally, the curve is a graph. Okay? So if you look at this curve, there's a couple of bad points, but otherwise, if you just zoom in close to your favorite point on this curve, you're basically looking at the graph of a function. So let's just take a look at this. If I take a point here, for example, if I just look at the part of the curve which is here and I forget everything else, this is the graph of a function. The fact that there are points below here now is irrelevant. So locally, it is a graph. So in theory, I can use exactly the same thing that I did earlier to find this. So, but the problem is if the curve, so here the curve is, the equation is very simple, so it could actually solve for y. But if I had an expression which is, let's say, x cubed y7 plus cos of xy equals to y power log of x, then forget it. You're not going to be able to solve for y in here. That's just too nasty, right? So something like that is not going to work out very well. But you can still consider y as a function of x, even though you don't know it explicitly, okay? So in general, cannot solve for y, but y is still a function of x implicitly. So you don't have an expression explicitly of y as a function of x. You can't solve for it, but you can still treat y as a function of x. You can see here, if you look at close to this point, it's the graph of a function. I don't know what it is, but it doesn't matter, okay? So this is, if you remember implicit differentiation, that was the idea. So let's just apply it to this very simple case, right? So let's say that I view y as a function of x. And I've got x squared plus y squared equals to 1. I can differentiate both sides. With respect to x. Okay, so I take the derivative with respect to x on both sides. Like that. So again, you can think of y as some unknown function of x, and you just write y instead. Okay, you can. This is just a big box, and inside is some big expression involving x, but you don't care. Okay. So I can differentiate this. That's easy, right? This is 2x plus the derivative with respect to x of y squared, and this is of course 0. Okay. So now, if you remember, long time ago, Cal 1, I've got y squared. Y is a function of x. It could be cos x, it could be whatever. So how do I do the derivative, right? It's a chain rule. So this is 2x plus 2 times the derivative, sorry. So this is 2 times y times the derivative of the inside part, which is dy dx, right, by the chain rule. I need to use the chain rule. Y is not x. Okay? And after that, I can solve and find that dy dx, so I'll just skip a few details here, but basically, this is minus x over y. And of course, this makes sense as long as y is not 0. Okay? So what does that tell us? Let's go back to our circle, right? So if you take a point xy on this circle, you can find the slope of the tangent using this expression as long as y is not 0. And you see, this is a very interesting example because y equals to 0 will give you precisely these two bad points, right? So these points are bad, right, in the sense that y equals to 0, or there's a vertical tangent, basically. But otherwise, everything works out. Okay? Okay, so you've done stuff like that a long time ago. What's interesting is that with partial derivatives, things get actually a lot simpler. So, okay, so now let's take a look at the following case. So let's say we have a curve, and it has an equation in x and y. So think something like x squared plus y squared equals to 1, or x cubed y minus xy squared plus cos x equals to y. Anything like that, okay? So you have some equation, and you plot the points, and you get a curve. Okay, now if you think of anything that looks like this, certainly you can rewrite it as follows. So you put everything on the same side, and you're going to get an expression in x and y equals to 0. So what's an expression in x and y? So it's just some function f of xy equals to 0, right? So you can do that for these examples, any example. If you have some equation involving x and y, put everything on one side, and it's going to look like that, okay? So this gives you a curve. Might be a complicated curve. Something like that, right? In the plane. And now, again, locally, except at bad points. So locally, except at bad points. We'll see later which one they are, but it's not a big deal for us. Then y can be viewed as a function of x. right? So if I take, let's say, a point here, look around this point, this is the graph of a function. If I take a point here, that's the graph of a function. Now, obviously, if the function is really complicated, you won't be able to solve for y. So note, usually, you cannot. I'll stop pretty soon. Usually cannot solve for y in terms of x. And we don't want to, okay? This is not something you wanna try. So obviously, if you look at the example here, if you try to solve for, actually this one is not too bad, but okay, so let's change it. There you go. Now try solving for y and you're not gonna have much fun there. Okay, so, but that's not the point. The point is that we can view y as a function of x. No problem. Okay, so I'd like to get, we want to find the slope of tangent at some point. In other words, what I'm looking for is dy dx. So how can I find dy dx? Okay, so let's take a look at this. Okay, so to find dy dx given f of xy equals to 0. Okay, so here's the idea. It's a very cute idea. So you have your function f, which is a function of x and y. And now I'm viewing y as a function of x. So if y is a function of x, this is a function of x, and obviously x is a function of x. It's x, right? So now I can apply the chain rule to this. Okay, so what does the chain rule say? It says, so if I'm taking the derivative on both sides here with respect to x, this x, right? So this will be del f del x. Now this is the x over here. You might rename it if this becomes confusing, but this is the x here. Del x, or actually, sorry, it's a one variable derivative, so dx dx plus del f del y, the y which is here, dy dx, and this is, derivative here, is 0. So I'm taking the derivative both sides with respect to x, that x, the little x here. Let's be fancy here. Okay. All right, so I just applied the chain rule with this setup here. Okay. So now one last step. So this is the same. So this is del f del x. What is that? It's just the function x with respect to x. The derivative is 1 plus del f del y times the dy dx I'm looking for, and this is 0. And this is what I'm looking for. So I'm going to solve for that. So I'm going to get dy dx is minus del f del x divided, sorry, that's not right. Del f del x divided by del f del y, provided, of course, that this thing I'm dividing with is not 0. These would be the bad points I was talking about. So this is what I get. Okay? All right, so let's just apply this to the circle. Of course, the circle is already very simple, but once we get to more complicated curves, then what you did in Cal 1 becomes a bit nasty, but with this technique, it's very, very quick. Okay? So let's see. So let's take a look at the circle. x squared plus y squared equals to 1. I rewrite it as f of xy equals to 0. So what is that? That's x squared plus y squared minus 1 equals to 0. This is f of xy. So what we found is that dy dx is minus del f del x divided by del f del y. And these are easy to compute, right? Del f del x, that's 2x. Del f del y, that's 2y. So here's what I get, minus 2x over 2y, which is, as expected, minus x over y. Okay? Okay, so I'm going to finish with one last example, which is a little bit more interesting than this one, but still very simple. Okay, and then we'll stop after that. If you have questions, please do not hesitate. Okay, so another example. Okay, so this is an example you actually probably saw in Cal 1. And it's a bit involved. If you do it with the Cal 1 method, with implicit differentiation, it'll take you like a few lines to do it. But with this technique, it's very, very fast. Okay, so here's the example. So find dy dx if y is implicitly defined by x cubed plus y cubed equals to 6xy. This is actually a pretty cool curve. Okay, so let's see. So I'm going to rewrite it. This is important as f of xy equals to 0. So you put everything on the same side. It doesn't matter which side you choose. But I'll write it this way. Okay. So this is my f. Okay. And what we saw is that dy dx is minus del f del x divided by del f del y. Okay. So let's just compute that. So del f del x is very simple. This is 3x squared minus 6y. And del f del y is also very easy. 3y squared minus 6x. Bingo, that's it. So if I want it at a specific point on the curve, all I have to do is just substitute x and y and I get the slope of my tangent. Okay, so look up this example in your Cal 1 notes if you haven't burnt them, and or look in the book and you'll see that it takes a little more work to do it with implicit differentiation starting from this. It's not a huge deal, but it's still much, much longer. Okay. All right. So next time I'll finish implicit differentiation. We'll do it for 3 variables, not just 2. And this will be the end of 14.5. Okay. And after that, the 14.6, which I'll start. And are there any questions, comments, anything? You're just as quiet as in class. Sorry? I can't hear you very well. Is it Olivia?
Yes.
Okay, yeah, I can hear you a little bit. Go ahead.
Will you be posting this online?
Yeah, I will, absolutely. The video and also the slides separately.
Okay.
Yeah. I hope you're all doing okay. We'll try to make the best of things. And yeah, I wanted to add something about the test. Um, don't worry. That's all I can tell you, right? We're all in this together, and let's try just to make the best of it. But I'm not going to. Okay, so one thing I want to let you know, obviously, I'm not going to, because you're doing your test at home, and it's an open book test. If these were normal times, I'd adjust the test because I know you have your books with you or whatever else you can bring in. But these are not normal times. So this test is going to be basically what you would have seen in class. And so please try not to worry, okay? So just if you do just the basic stuff that you're supposed to do, you will be fine, all right? Okay, so by the way, this is actually a pretty good way of answering questions. So rather than Mio, which is not working very well, by the way, if you send me a message and you want me to write stuff down, we can just meet through Zoom like this, and we can exchange stuff that we're writing. That's fine. Just let me know, and we can set up meetings. So. Okay, so if there's nothing else, I'll see you, I guess, Wednesday. And thank you for being there. Good luck.
Thank you.
All right, cheers.